Hey there, my name is Ben Rodney from ASHRAE New York, and I want to welcome you to this episode of the ASHRAE New York Designer Series and the brand new ASHRAE New York YouTube channel. We'll be bringing you educational content, interviews, and chapter updates, and it'll be open to members and non-members alike, or anyone just interested in the HVAC industry or updates on our chapter. You can find us on LinkedIn, Instagram, and make sure to go to our website, ASHRAENY.org, where you can sign up for our newsletter, check up on chapter events, and hopefully even join us as a new member of the chapter. If you like what you see here, make sure to hit the subscribe button below this video and then hit the bell to get notifications on any future updates to the channel. If you have any comments, questions, or conversation about this video, just leave them in the comments section. Thank you and enjoy the episode.
All right, good afternoon, everybody. My name is Ben Rodney. I'm with the ASHRAE New York chapter. We're really excited to have you attend our first episode in the ASHRAE New York Designer Series, a brand new webinar series over the next 6 weeks where we have representatives from numerous engineering firms here in New York City that have generously volunteered their time to present to our members as well as other members of other chapters in the region. We have a great lineup coming up for the next 6 weeks, and I just wanted to go through a few housekeeping items before we get into the presentation. If you can see on my screen that as part of the, let me just make sure I'm sharing my screen. Yes, so as part of the requirements for the PDH, we have to have a Q&A. So if you have any questions, there is a questions tab on your display screen. If you just type in those questions, we'll pick a few of them at the end and have the presenters answer those. For the PDH, at the end of the presentation, there's going to be a poll. So when you log out of the GoTo, you have to answer that poll in order for us to get your information so that we can show the Practicing Institute of Engineering that you attended and they can keep your records appropriately. So you'll be sent your certificate automatically within the next week or so to get your credits. We'll also send a survey at the end of probably tomorrow to ask about your thoughts. So for any more information, just go to our website, ASHRAENY.org. You can get the schedule. So next week we also have a presentation on stack effect in tall buildings, and the next designer series is going to be on fire and smoke dampers in healthcare facilities. So without further ado, I want to introduce Shannon, Kaplan, and Brendan McGrath from AKF to present their net zero energy case study.
Great, thanks, Ben. All right, everybody, I'm just going to get this switched over to our presentation. All right, we should be all set. Brendan, can you confirm everyone can see the screen?
Looks good to me.
Awesome. All right, well, thanks everyone for joining us. Again, my name is Shannon Kaplan. I work at AKF. I will be talking to you about the design side of the HVAC systems for the Lombardo Welcome Center at Millersville University, which is a project that we worked on to design for net zero energy. On this project, I was the MEP engineering project manager, as well as worked on the renewable energy and net zero energy consulting as well. Brendan, who is with me, will also be sharing some findings from construction and commissioning. Brendan worked on this project as the head commissioning engineer, so got a lot of chance to really put these systems through their paces. All right, so we're going to get started here. First, as Ben mentioned, this is available for continuing education credits, so we are obligated to provide a course description. Here it is. I promise we'll talk about all these things, as well as learning objectives. We have 4 learning objectives for this. If you have any questions about these learning objectives or course description, you can always follow up with Ben. All right, so we're going to get right into it. This project is located at Millersville University, which is a state-funded university located in Pennsylvania outside of the Lancaster region. So it's a fairly rural area that doesn't necessarily have a ton of exposure to some of the sustainability features that a lot of the bigger cities are seeing in terms of buildings. The project site that we're looking at for our project is actually right here at in this photo, it was a barren field. They had demolished a dormitory, but this is really right towards the heart of their campus. You can see over here that there's to the right of my arrow is a building that's the student dining facility. To the right of that is the student center. Behind this site is all of the dormitories, and across the street is where we start really getting to all of the classroom buildings. So this project's really at the focal point of their campus and was designed to be their new welcome center, as well as home to the housing group as well. Just zooming in specifically on this site to give you a little context about the project, but this is what the final siting looks like for the building. As you kind of come down the main street and turn, you'll have a great view of this building and be able to really get a sense of what Millersville University is about. And one of the goals, as I said, for the owner was to make sure that this really stood out as an example of sustainability. As part of their sustainability goals, the university made it clear that they wanted this project to be seeking out zero energy certification from the International Living Futures Institute, which one of the requirements of that means that it has to be a combustion-free building. So when looking at mechanical systems, we were looking at systems that would be able to run on electric. Part of their goal for the net zero energy certification was also to prove their commitment to the climate action plan that they had recently signed and try and help their campus reduce their overall energy footprint and carbon footprint. Taking a look into the building, the final building plan ended up being a one-story building that houses over on the left with blue a classroom and presentation room, which is used to stage presentations for incoming prospective students, but is also a space that anyone on the university or in the larger community can request to rent out and use. In the kind of golden color is a large central lobby space, which is also not just a pass-through on this building. However, they do want it to be a connector, and it has become a connector from residential to classrooms. It's also a staging point for all of their future student tours. Within this lobby, you can kind of see on this long wall, there's also a series of dashboards that give you information about the university, as well as an energy dashboard that shares a lot of information about what's going on with energy in this building. And we'll take a look at that dashboard later on in the presentation. The remainder of the building is really just typical office space. These are color-coded by department, so you can see they have the admissions offices here that deal with all those prospective students. We've got student housing on the lower side. We also have the marketing department because all three of these departments fall under the same vice president at the university. And then in green are the shared central spaces such as conference rooms and kitchen areas. So at the end of the day, it's really mostly an office building, one story, not too large, with ambitious goals. I will note that the way that the project ended up working out and the way that the site works out, there is a steep slope that lowers down to the right of our screen. And in that area, we were able to put in a lower level MEP basement only. The way that the site slope works is this was actually able to be a walk-in basement, but it became dedicated for just our building systems, which provided us with plenty of room to put the equipment that we needed for all of the trades. Just to give you a sense of what the finished building looks like, this building was completed in 2018 and was occupied starting in February of that year. So it's been in operation for 2 years at this point. So we have a lot of great information on the energy and the performance of the building. Just to give you a quick look, this is a shot inside the classroom in the upper left. To the upper right is an outside picture of what you see when you're coming down that main road of what the building looks like. The lower right corner is a shot through one of the long corridors in the office space. And then the lower left corner is a look through that lobby where you can see those energy dashboards and other displays for Millersville. All right, so getting into the actual design of this project, with any time you're going to look at a low energy building or a net zero building, one of the first things that you really need to focus on is energy efficiency. We can always put more photovoltaic panels in to generate more energy, but one of our goals here was to keep all of the panels on the roof of the building. They didn't really want to clutter up campus. They didn't want to make claims of net zero energy by simply sticking PV on the parking lot across the street. So we really wanted to make sure we understood how this building was going to perform. We went with a lot of the typical strategies, really focusing on the building envelope and its performance, making sure we understood the siting of the building and how that could help us maximize energy generation and help us take advantage of some of the free heat in the winter. We took a look at energy efficient lighting and daylight dimming controls, and we spent a lot of time focusing on what would be the energy efficient HVAC systems. I just want to touch on the building envelope strategies really quickly because they do have a significant impact on some of the choices and system sizing for the HVAC system. So for this project, there was this careful balance between wanting to have a very well-performing building envelope, but also the need to create these very visible spaces that seemed transparent and really welcomed in students and prospective students. So as part of that, we spent a lot of time looking at the performance of the curtain wall sections that we were going to have, really paying attention to not just the glazing, but what the thermal bridging would be in the framing. We really spent a lot of time and effort making sure that we got that whole system to perform as well as possible. In addition to that, we did a lot of work with making sure we had quality insulation on the more solid parts of the building and took some measures to put in some daylight strategies that were going to provide shading for glare control, but also to eliminate some of that unwanted solar heat gain in the summer months. So all of that was on the south facade. All right, so moving into our HVAC systems, really at the end of the day, we like to do an evaluation when we're coming into one of these net zero projects. We don't want to just assume that there is a set system that's going to work. Really, this is a conversation with the owner, and it's going to be based on several factors. What do we need to do in terms of energy savings? What kind of systems are they going to be comfortable with maintaining for the duration of the building? Because we need this to run well, not just day one, but through the lifetime of the building. And then what's the cost and how is that going to impact things? When it comes to system selections for net zero energy buildings, one of the interesting things is that the cost equation gets changed from what we normally think of. Normally, you would think the first option up here, the packaged rooftop with VAV, very standard spec office building system, would be the cheapest up front. However, in net zero, you have to remember that you're also buying all the solar panels that are going to make all the energy. And if that system uses significantly more energy, we're going to need to purchase significantly more solar panels day one. So that gets tied into the cost of the system, which kind of changes our equation. But typically we like to look at all the way from the very basics of the packaged rooftop with VAV through other options. Again, this is a smaller building, so we're looking at mini splits, VRF systems, and geothermal systems. I will tell you which system we used on this project, but I just wanted to share this first because it's very interesting. We've actually recently worked on 2 different buildings that were both trying to achieve net zero energy. One is the Millersville Lombardo Welcome Center that we're talking about today. The other is the Sustainable Energy Fund, which is a spec office building. Sustainable Energy Fund will be an owner and will have a small space, and they are treating this as a commercial building that they will be renting out to other tenants. These 2 owners are in generally the same geography with a lot of similar strategies that they're looking to go after. They both want to be net zero. The buildings are almost identical in size. They are both 1-story buildings, and they are both primary office with 1 classroom. So huge similarities here. However, where they deviate is the owner's goals. The Millersville Lombardo Welcome Center project really wanted to showcase technology and highlight what's possible to the community. So therefore, they were really interested in what are the systems that are really going to be different and unique that people can come and learn from at this building. The Sustainable Energy Fund building really wanted to prove that net zero energy could be commercially viable, and that within a reasonable term of payback, that they could build a building that would be net zero energy, and on those energy savings, make a reasonable return in their investment. So they were looking for systems that were going to be energy efficient, but also very cost effective upfront. At the end of the day, where each of these buildings went was in a different direction. The Millersville Lombardo Welcome Center ended up going with a geothermal well system with water to air heat pumps and had those ducted to various spaces. And after doing much study, ended up with a whole building DOAS because there was a lot of efficiency in being able to share the variations across the spaces on that DOAS. The Sustainable Energy Fund project ended up with a VRF system with individual fan coil units across the many spaces. These could be scaled up as needed across the future tenant spaces as they get divided. And they have distributed very small ERVs to provide the ventilation, again, to allow for some of that flexibility, but also to manage some of the cost. So when we're talking about these systems, we don't like to go in with just a preconceived idea, but we really like to talk to the owners. A part of that conversation also gets into discussion about strategies such as where are we going to locate some of this equipment. So for Millersville, our goal was to make as much energy as we could on the roof. This meant sticking a large DOAS unit up on the roof was not going to happen. Plus, it's a one-story building, so the view lines were pretty tough. We did take a look at what were the differences between putting this unit outdoor and putting it indoor, but at the end of the day, they couldn't really find any locations they felt were a great spot to stick this large unit out on the ground. And with that slope that we had, we were able to create that basement. So we did end up opting for an indoor unit here, which left our roof free for more PV and still hid the unit from the average person walking around the building. We also spent some time working with them, not just on how are we going to generate the heating and cooling, but how are we going to distribute this air? Again, there are a lot of options out there. Depending on what you pick as your main system for generation, you're going to be looking at different distribution options. And once we had narrowed down to geothermal, it seemed like the obvious choice was going to be the water to air heat pumps. However, we did talk about what some of the other options were that we could have, other strategies we could take. At the end of the day, Millersville has their own facility staff, and they wanted to make sure they were left with something that would be easy for them to maintain. So they didn't want to get into too many, as they said, quote, crazy systems that they would have to learn to maintain. So they did end up with the water to air heat pumps. The only deviation from this was where we had that large curtain wall glass in the lobby. We did end up with some radiant floor simply to help with the cool temperatures from the glazing in the winter, because there's a lot of seating in that area where we expect families to be sitting as they're waiting for that prospective student tour. When it came to the geothermal well system in this location, it's really not that common in this area. One of the reasons is that the soils in this area and the bedrock is limestone, and that tends to have a lot of voids in it, making drilling wells tricky. If you end up starting to drill in a designated location and hit a void, the well driller is going to have to back out because it will not be possible to complete that well successfully and be able to fill it with the slurry. It will just end up filling out the void, and it will take a lot of extra slurry and not perform as expected. So the president of Millersville really did want to make geothermal happen here. So one of the strategies we undertook was that although we only needed 20 wells to serve the building, we ended up with a design layout that included a surplus 10 wells. This meant that as the driller got out there and started drilling into the ground, if they hit one of those voids, they could simply back up and know exactly where else to go. It actually turned out that this site was very lucky, and during the drilling process, we hit really, I think maybe only one void. So on the whole, the well field as designed was able to be installed. And as a means of helping people understand that this is what the source was for heating and cooling, the university also designed these little markers that go into the ground and in the pathway to show people where those wells are, because it's a hard concept for a lot of people to visualize when all the piping is underground. One of the other things we really had to think about when we were looking into the mechanical system, the design, was to really understand the schedule of this building. Unlike a traditional office building, which is going to have office hours between like 7 in the morning and 6 o'clock at night, this program serves all of these student tours and also serves the housing for all of the students, which has move-in days on weekends. So when we started to understand their schedule, we found out that there was a lot more steady weekend use. And there were also some staff that at certain times of the year ended up working crazy hours. One of the women in housing said that sometimes she was known to stay there for 24 to 36 hours in a row. So thinking about the conditioning of this space was a little different than a standard schedule. And we also had to understand that each of these departments would be running on different schedules. And all of this was going to impact how the systems were going to be set up and how they could be running. At the end of the day, we came up with a huge number of zones for the mechanical system. We did keep the presentation room on its own zone highlighted here in orange. There's also some restroom facilities outside of that presentation room that were able to be on a zone. The lobby is a separate zone. There's a lot of temperature fluctuation in there due to the amount of curtain wall glazing. So we wanted to be able to control that. And as I mentioned, there is some radiant flooring located on both the north perimeter and the south perimeter, where there are seats available for people to hang out while waiting for a tour. We also did some centralized zoning for the core areas, and then we divided all of the office spaces up, with each open office area getting a dedicated unit. And in the final design, we had just a few offices, no more than 3, shared on a single unit as well. So how did we end up with that kind of zoning and design? Well, What always happens on these projects, I find, is that you start out in schematic design, you're working on a basis of design, and everything seems really simple. We know what we want to do, we're going to set about doing it. Once we decided on geothermal, we thought it would be most ideal and energy efficient to have one heat pump per office, one heat pump for as many of these small rooms as we could, so that they could really modulate themselves and only serve what they needed to based on occupancy and other factors. So this led us to a design of 40 individual heat pumps ranging from a half ton to 3 tons. Each one would have its own dedicated thermostat control. And at this time we weren't sure, but we were looking at either horizontal concealed or vertical units located in closets. This is part of our maintenance discussion with the university as well. By the time we got through design development, there had been a lot of cost analysis, and as is frequent to happen in projects, amazingly, the project was over budget after schematic design, so we had to make some tough choices. Part of this came in the total area of the building, thus eliminating any potential for these vertical units and closets. We really needed that square footage. So we were now tucking all these units into the central core area where we had ceilings, as opposed to out in the office areas where we didn't have ceilings. And we also looked at a strategy to cut down on the number of heat pumps in order to save some costs on the mechanical system. At this point in the design, we were down to about 20 heat pumps, with that up to 3 private offices on a single heat pump, and looking at the strategy of just 1 thermostat per heat pump and having that diversify across the offices. Of course, this got some backlash. As part of this project and net zero, we wanted to make sure we were engaging the occupants. They were all existing staff on campus, and we spent a lot of time talking to them about what it would mean to be in this building and how they as occupants would be making choices that would impact the energy use. And those choices included things like what you plug in and what you do with your thermostat. Well, the staff on this campus were coming from a converted dorm building that had been converted into private offices, and each of them had their very own lovely PTAC unit in the wall and were able to control their office. We spent a lot of time talking to them about how we wanted to be efficient, and really at the end of the day, most of these occupants were really concerned with, is it going to be effective? Am I going to be hot or cold? And a lot of these occupants expressed that they tended to run hot and were really worried that the building would be too warm. After that conversation, somehow a vicious rumor got started amongst them that the design team was going to have the building set point in the summer at something like 80 degrees, which was never the case, but you know how rumors go. Once they get started, they're hard to squash. So we did come back in and follow up with them, and we actually wanted to really understand what some of their fears and needs were on the thermal comfort side of things. So we did come up with a survey that we sent them. Part of this was to really understand what were their off-hour schedules. You know, it's one thing to control what the HVAC system is doing during standard business hours, but what people expect to happen in off hours can be different. I know if I come into my office on a Saturday, well, back when we could go into the office, you know, that I wouldn't have expected it to be the same temperature as I expected it to be on, say, a Tuesday morning when I walked in. I knew that on the whole, the building was unoccupied that Saturday, and therefore I expected the systems to have let the temperature ride a little bit. So we wanted to understand what their off hours norms looked like and what their expectations were. And it turned out that most of them were totally fine letting the systems ride in the off hours. We also wanted to understand what they were used to in terms of their own controllability and measures they would take to stay comfortable. And we actually found that 52% of these occupants were willing to take extra steps to ensure their thermal comfort, and 45% weren't going to do anything. So we really wanted to make sure we understood how to keep those 52% that were going to take extra action, especially the ones that might plug in fans or space heaters, which will introduce more energy, to keep them comfortable so that they wouldn't need to take those steps. So after talking with them and the university was curious what it would mean if we did support those additional off hours with extra HVAC system usage. We ran this through our energy modeling and found out that this would increase the total annual energy usage by 7.7%. So at that time, it was decided that we would simply go with a 1-hour override system. The occupants could get the heating and cooling if they really needed it, but we wouldn't account for that in any of the scheduling. We also followed up with the occupants and shared some of our other findings and our changes in our design strategy. As part of this, we ended up deciding that we would provide thermostat locations in every single office. We would change the way that the systems were ducted to allow for each office to respond individually. We agreed to temperature set points of 74 degrees in the summer and 68 degrees in the winter, with thermostats that would allow the individual occupant to go plus or minus 2 degrees. We also told them and gave them a lot of information on the fact that this building would have humidity control that would be cutting down the humidity in the hot summer months, which is something they didn't experience in their building, and we assured them this would help them feel more cool. They were skeptical about it, but it turned out after being in the building through the first summer, many of them did come back to us and say that they actually could feel the difference, and they were much cooler in the summer than they had ever thought they would be. We also talked about not opening windows to help with some of the energy efficiency and letting the systems do its job. And again, I mentioned the after hours became a 1-hour override that they would have to manually opt in for. So as we wrapped up into construction documents, we ended up with more of a finalized design that had up to 23 heat pumps. We now had a thermostat in every office, and we introduced this bypass VAV concept to allow each office to have its temperature control by its own thermostat. When we got into construction, there were a lot of RFIs about this bypass VAV design. It turns out there had been a similar but different design elsewhere on the campus, and the same contractor was involved, so they kept confusing the two systems. That confusion led to the sheet metal shop drawings, which we had to review several times in order to ensure that we were really going to get the system configured the way that we wanted. And again, we had to make some adjustments and compromises and tweak the design. So at the end of the day, what started out with this simple dream of a really nice geothermal system with these water-to-air heat pumps ended up being a lot more complicated than we wanted. But we knew that in the back of our minds, the goal was still to make sure that this system would be saving us the energy we needed to save and would meet the occupants' needs. During the course of this, we did a lot of energy modeling, and we're constantly trying to predict what the annual energy use would be and how much energy we thought we could generate on the roof. So this means that we were also looking at it down to the systems, including the mechanical system. Our overall goal to ensure that we hit net zero energy in the first year was to actually aim for net positive, which meant we were looking to carry a contingency of up to 20%. At the end of the day, our goal had been to do this on the roof, and we found that our predictions were showing us the roof would provide 17% of our contingency. So as long as the systems performed as expected, we would be fine. However, the university, as I mentioned, wanted to showcase technology. So they did end up including a PV tracker, and they ended up including glazing along the southern facade that actually generates energy. So that got us to a final planned prediction of generating 127% of our annual energy. With that, I'm going to turn it over to Brendan to share with you some findings from construction and operation.
Thanks, Shannon. So bear with me as you hear any child in the background or a dog bark as we go through this. I'm also presenting Shannon's screen, so there might be a little bit of a lag here. So I know that this webinar is called Designing to Net Zero, but I want to kind of expand on that because just good design doesn't get us to net zero. There's quite a bit more that has to take place in order to get there. I'm going to argue today. So part of that are the occupants. Part of that are the operators. There's a level of quality construction that has to happen. And as a commissioning provider, I'm also going to argue that commissioning can really be a big advocate to get you to net zero. There we go. So as Shannon mentioned, I think this is a bit more than the traditional design. There was a lot of workshopping that took place pre-design. This wasn't, hey, we want a 15,000 square foot building for a couple of user groups in a classroom. Let us know when you're done with it and we'll build it. It was a lot more than that. They were literally able to interview the specific people that were going to occupy this building. And that gave them a leg up to really understand their needs and meet their needs in an efficient way. The design here really queued us up for a successful building in a number of ways, which I'll get into. As Shannon mentioned, this is Millersville University, so this is a state-funded project. Millersville procures buildings in a multi-prime fashion. So anybody who's been involved in the construction industry knows that there are inherent challenges with a multi-prime contract. One contractor says it's not their fault, the other contractor says it's not their fault. I don't know whose fault it is, but we got to get to net zero, so let's try to make it work. And then finally, commissioning was a big part of this. And in fact, you know, the bulk of the work that I do is standard new construction commissioning. You know, we have our checklists, we have our functional tests, and we come in and we get our issues in, and then maybe we walk away. But here, I think it took a little bit more than the standard commissioning process. So as Shannon mentioned, we did have an energy model. So how do we bring that energy model to reality? An energy model is great. It tells us a lot. It's a great predictor. But what are the assumptions? What are the key assumptions that really had a big influence on energy that went into the energy model? Knowing that this building was you know, working towards net zero energy, I had those kind of thoughts in mind as I went through, thinking about the functional testing and the checkout of the systems. And I actually consulted, you know, because we did the design and the commissioning on the job, I was able to literally have a direct connection to the energy modeler and try to tease out some of those key assumptions that went into the energy model and make sure those assumptions ended up in reality. And that did end up differing in some instances. I'm going to get into that in just a minute here. So persistence, as I said, a little bit different than your standard commissioning process. There's a level of persistence. Now that can be done, you know, with a relationship with the commissioning provider. That can be done with a savvy control provider. If there's an energy manager on campus, you know, that can be done with them. But there is persistence here, and it's not just about how the system works at a single point in time. It's really about how that system performs over time. And if we see deviations from expectations, how do we go about actually rectifying that scenario? And the occupants, of course, the occupants are important here. Sometimes they, you know, in building design, we don't give the occupants any control. Sometimes we actually give them fake control so that they feel like they have some level of power related to their scenario. In this case, we gave them real control, but that was part of how we were meeting the needs of the occupants, but also designing an efficient system. So not only do they have control over their own destiny, they can literally see the impact of making change on the spaces. So if you look here, the larger picture on the screen there, that is the lobby. This Lucid Dashboard is available on a big touch screen there, so you can literally track energy in real time. Not only that, we did have a little bit of an ace up our sleeve here. The sustainability director for the whole school, his office is in this building, and the other occupants are well aware that he's there. He's an advocate for getting us to net zero, and I think he was instrumental in taking us on that journey. So back to our energy model. This gives us a boundary. This gives us an order of magnitude. We can see here, there's a couple of things I want to point out. You know, the split between end uses of plug loads, lighting, and HVAC were almost even, almost a third, and a third. The EUI predicted by the energy model was 36.7. And if we look at the seasonal profile, there's not an extreme seasonal profile to the building according to the energy model. So that gave me some bounds to think about as I was reviewing some of the trends that we went through. Similar with the renewable energy system, I know that this is ASHRAE and this is HVAC focused, but we couldn't get to net positive energy without having a renewable energy system. In this case, we have, as you can see here, and Shannon mentioned, the roof is pretty much covered end to end with solar panels. Not a lot of room for anything else up there. In the center, we have the flat on the east and west sides, and then we had a couple of extra systems that were really kind of educational in the vertical glass and the dual axis tracker. And then if you look at the pie chart, you can see that clearly most of our energy is being produced by those two main systems on the roof. So without the right tools, I really wouldn't, myself and really the project team, Chris, the sustainability director, we really wouldn't be able to track to where we were going, where we wanted to be. We really wouldn't be able to do analysis and diagnostics on the systems without the right tools. So Shannon Kaplan was the project manager for the job, but also the electrical engineer. She set us up really well with a number of meters, and actually we had more meters than we could even deal with. So there was a level of integration that had to happen there, and ultimately those went into that live Lucid Dashboard, which gave us real-time feedback, and then we could do some analysis, and I'll show you some trending on that in just a minute here. But we were set up well from the design, and then I took it as my job to take it to the next level, to do that analysis and understanding really how we were doing versus how we were predicted to do. All right. So this is an overview of the monitoring action plan for the facility. There is a Lucid Dashboard, which I've shown, and I'll show you a little bit more on. We did do tracking by end-use HVAC, lights, plug loads. We got into some pretty decently deep critical system tracking, which included the HVAC system specifically, and also the renewable energy system. We then, through that tracking, we were able to identify some deficiencies and opportunities for improvement. There was some root cause analysis, and there was an interesting finding that I'm going to show you in a minute. And ultimately, where we wanted to go was net positive. So here's the Lucid Dashboard. I've worked with a lot of owners that they have these pretty amazing tools. They have access to energy information, but they're very hesitant to actually share that with anybody. That was not the case with Millersville University. As soon as this dashboard was configured, it was live and available to anyone. So this is a fully transparent platform. There's a number of different ways to look at the energy use and the energy production of that facility. You can do a Google search for Millersville University and find the Lombardo Center, which will link you to this dashboard. So this is open and available for anybody that cares to look at it. As well, it's literally displayed on a giant monitor in the the lobby there for this Welcome Center. So any new students, any parents, anybody that comes into the building is able to look into that. So that was part of the strategy and the way that we could track energy here. So how are we doing? One of the things that jumped out to me as I went through this first year evaluation was that we had some differences in terms of the end-use breakdown. So before we were relatively even between plugs, lights, and HVAC, but in fact, when I took a harder look at it, based on actual data, what I found was that plugs were less and lighting was less and HVAC was up. So, what tells us where we really are is the EUI. If we look at that EUI, we were actually tracking towards 26 rather than 36. So tracking very well, but still it was curious, and I wanted to know more about, are we high on HVAC? How are we doing on lights and plugs? Like, what's going on here exactly? That led me to some of the critical trends that we looked at. This is just an overview of the critical trends. We looked at them from a high level. First with just overall HVAC consumption. I then wanted to verify a number of energy saving strategies. This is ASHRAE, so I'm sure you guys are well aware of the push-pull between indoor environmental quality and energy savings. So I wanted to make sure that, based on available sensors and data, I was able to at least kind of verify that we were meeting the air quality standards that we wanted to. I wanted to take a hard look at thermal comfort because I know that occupants and operators will make it work one way or another, so regardless of the energy impact. So I wanted to make sure that we were actually meeting our thermal comfort requirements for the building. And then finally, I wanted to kind of just take a look at how the interaction was between energy savings and indoor environmental quality. So here we are. My focus really for the facility, due to just the contract with the owner, was to focus on HVAC systems. However, I couldn't help but take a look also at the lighting and plug load. So If we look in the upper right graph here, we can see that lighting is way low. So why is that? You know, some of the investigation there told me that our modeling platform actually doesn't do a great job of actually estimating daylighting controls. So in fact, our daylighting controls are working a bit better than we had originally thought or accounted for. The plug loads, we literally know that they didn't install their full energy budget of plug loads. There's a copier that wasn't installed, and there were some other items that just literally weren't installed. So we're actually using less energy than we would have for lighting and plug loads. So we have less heat being produced inside the building. So now our HVAC system has to make up for that. And that doesn't totally explain why we were over on HVAC consumption. I looked at that on a monthly basis and tried to identify the outlier months. I want to take a second here to try to explain this graph. If we look at the blue line, what we see here is that we have the months, and then we also have the percent difference between the energy model, the original energy model, and what the actual consumption was of the big building. So we can see we have some outliers in July at about 30% different from the energy model. October, November, January, February were between 30 and up to almost 50% different from the energy model. So since I did have access to the energy modeler and he was very interested and willing to participate in this analysis, you know, I said, okay, well, I know that we use 30-year weather data in an energy model. What if we use the real year weather data? What does that do for us? I also looked at some of the other assumptions that went into the energy model, including set points and minimum set points related to the equipment, and how does that affect the energy model? So he was actually able to do a light calibration of the energy model and get us a bit closer. So you can see that October, November, January, and February really came down below 20%, but however, there was still a significant outlier, which actually got worse, which was July, is now up above 40%. So then I said, okay, well, let's take a little quicker look at July. Now we do have in the controller here, we have a spot for questions, but if you can actually answer this question before, let's see here. There is a question up here already. You can put in here what you think about what happened there. You're not going to get much, but you get an attaboy and a virtual pat on the back. What we're looking at here is outside air temperature, and then also electricity consumption of the facility. This is, as Shannon mentioned, it is pretty much an office schedule, but there are some nuances to that related to the annual schedule of those different user groups, and then also sometimes they just have crunch periods where they have to end up working a lot, 32 hours allegedly. So, but what you can see here is a pretty distinct weekly energy consumption profile where Monday through Friday is high, Saturday and Sunday is lower, and then you can see a baseline energy consumption that just continues 24/7. I don't know if anybody put anything in the comments there, but I'll give it away. In July, there was actually an override related to the schedule of one of those three user groups, which put it into 24/7 occupancy. Now, I don't know if that woman was just living there 24/7 or what the root cause of that was, but the suggestion here and the opportunity for improvement was some level of automatic turnoff for schedule overrides or an alarm related to manual schedule overrides. Which brings us to back to some of our energy savings assumptions and evaluation. So what we can see here, there's a couple of graphs. The important thing to understand here is that we're looking at the condenser water pumps, which are really part of the heart of the whole system. So, as I went through functional testing, bringing in some of those assumptions from the energy model into things that I was verifying during functional testing on site, something as simple as pumps literally turning off. So if all zones are satisfied, no compressors are operating, the heat pumps, we don't need the pumps on. So I needed to make sure that I took it to do a check to say, do we really have that in the programming, or are you just running those pumps at minimum all the time? So what we can see here is on the left lower graph, we can see actually that the pumps are turning on and off on a daily profile. on the right, the heat pumps are actually having to work a bit more. So we can still see kind of a daily profile, but the heat pumps are actually having to work more, but they are still turning off for some number of hours in the middle of the night. Interestingly enough here, I took a look back at minimum pump speed and what was the assumption related to the energy model. It's a little bit hard to see here, but the minimum pump speed in the actual building is close to 65%. It's not down at 20, 25, 30%, like what we had in the energy model. So that was one of the calibration notes for our calibrated energy model. So we are actually using a bit more energy here than what the model predicted. So that tells part of the story of why our HVAC system is using more than the prediction. Again, what's important, I had access to our geothermal well designer, and I asked him, and I said, you know, if you had the ability to look at a system operation over time, what would you really care about? He said, well, you know, I would really want to make sure that my well water temperatures weren't drifting over time. So this is only the first year of operation, but we could come back and look at 5 and 10 and 20 years and see that that well was either staying between consistent temperatures over time or having a bit of drift to it. Here, we're actually between 45 and 70, so as far as the first year operation goes, we were well within our limits and our expectations of what that geothermal well system is doing. We have the opportunity here to do persistence into 5 and 10 and 20 years. Again, a little bit of a confusing graph, but I'll try to explain it here. We have standby temperatures for all the zones. There's a level of integration between the lighting control occupancy sensors and the temperature set point control. So we don't just have an occupied space temperature set of set points and unoccupied space temperature set of set points. We actually also have standby set points. And this wasn't an HVAC only control method. We actually had integration with the lighting control system. So now I can't, unless I sit there and watch for where people are going and how the occupancy sensors are working, I can't tell that this sawtooth that we're seeing here is specifically 100% accurate. But what I can see is that we were, on a regular basis, we are going back and forth between the occupied space temperature set points and the standby space temperature set points. So that gave me a level of confidence that things were working pretty decently here. This was kind of a simple one, essentially a storage room that's unoccupied all the time, but it would be easy enough for a controls vendor to see that room and just put it on the same occupancy schedule as everything else. So what I wanted to do going through functional testing and verification was to actually make sure that we had the space pretty much unoccupied all the time, and then occupied when we had an override from the space thermostat or a lighting sensor. And you can see we do pretty well here. We kind of erratically change set points, and which is related to occupancy sensor. So this is air quality. We actually only have one CO2 sensor in the whole facility. We have a nice HVAC system here where we have the ventilation decoupled from the heating and cooling. So our dedicated outside air system generally provides constant volume of outside air to zones, except for one zone where we use demand control ventilation. So what I saw here was that the damper for that one demand control ventilation zone seemed to be working pretty well. But I thought, you know, there was an opportunity here to do additional verification in those other zones that don't have CO2 sensors. And the opportunity for improvement here would be to install CO2 sensors for tracking purposes in those other zones to make sure that the outside air is actually meeting the needs of how those spaces are being occupied. So as Shannon mentioned, we went from a relatively simple system to, you know, not a super complicated system, but a somewhat unusual system. There's a level of complication to it for sure. We have 2 individual offices in certain cases, served by one heat pump. So they're not, the internal loads of those two spaces aren't always exactly the same. So the way that AKF approached that was to provide VAV boxes downstream of the heat pumps. And there was control related to, well, is the heat pump in heating? Is the heat pump in cooling? And how do we manage the needs of both zones at the same time? So this bypass VAV control scheme came into play. So what I wanted to see here was that, well, first and foremost, are we maintaining space temperature set points in the zones? And then, you know, system related, are the dampers actually working the way that we think they're working? And generally, I did see the dampers working opposite of each other. And generally, I did see that the zones were controlling pretty well within set point. So although slightly more complicated than what we would have liked, my take from this was that we were actually satisfying the needs of those spaces. Zone thermal recovery. So the worst thing that you can have happen is to come in on a Monday morning, your space is cold, you're pretty much cold all day, and it doesn't even, the space doesn't even recover till, you know, that Tuesday. You know, but at the same time, it's important that we don't just throw that out the window and go to a 24/7 schedule. So I wanted to make sure that our morning warm-up scenario was working decently well here, and I actually did a little bit of an analysis on a very cold winter day. The temperatures here, I think, were like 10 to 15 degrees outside air temperature, and what we saw was that there was decent recovery on the north open office area, where we were recovering from the setback temperature of 59 up to 70 by 9 a.m. The schedule's really 7 a.m. So I do think there's an opportunity to improve this morning warm-up scheme. But if you're recovering by 9 a.m., to me, that's pretty good, and we're doing a good job of our morning warm-up. Although there is some opportunity for tuning there. So how do these things all interact with each other? Outside air has a direct impact. Indoor environmental quality and the outside air introduction has a direct impact on energy consumption. And this illustrates it decently well here. So it's a cascading effect from the zone lighting control occupancy sensors to the outside air damper to the spaces back to the energy recovery ventilator, which is actually a heat pump. And then that heat pump needs to have condenser water flow from the condenser water pumps. So if any piece in this puzzle isn't controlling properly, that could either lead to poor indoor environmental quality or excessive energy consumption. So it's important to understand the integrated effects of the control and the checkout and the check of the system. So relatively interactive. So that brings us to revisiting our predictions, and I'll let Shannon wrap it up. Shannon, you're on mute.
I realized I was on mute as soon as I started talking. Thank you. All right, thanks, Brendan. Yeah, so as you can see, there was a lot of teamwork going on between the design team and the commissioning team on this project, and we really felt that that was part of what helped keep this super successful. I will say that we did also spend a lot of time working with the contractors as well. And we did introduce to them our goals of net zero energy right at the beginning. So everybody was kind of always keeping an eye on making sure that our systems were going to be installed in a way that would perform as we predicted, because we did all really want to make this net zero energy goal. So at the end of the day, we've been keeping an eye on this. Like I said, it's been in occupancy for 2 years at this point. So we've been through 2 full calendar years of tracking. And I'm really happy to announce that not only have we achieved our net zero energy, we've actually been consistently performing as a net positive energy building. And we did achieve net zero energy certification through ILFI last year after our first full year of tracking. So overall, the university is exceedingly happy with the way that this building has been performing. It turns out that based on how the weather has been, the renewable energy systems have been producing more than we had predicted. We've also had some very low snow years, which has been helpful. And as Brendan had highlighted, our lighting and plug load systems had been performing much better than anticipated. And after some of the work Brendan did, the mechanical systems were also very tuned to perform well. So at the end of the day, we've ended up generating more energy and using less energy, and have come up with, and I'm not trying to pull a everybody's at home now thing on you. This is currently, as of earlier this week, at 196% of its annual energy. I get that March and April were a little low on attendance for occupancy in the building, but we did check this out in December, and in the December previous years, we were actually at 205%. So there is variability based on weather and what the building's doing, but overall this has been regularly trending significantly positive. And since this building is part of their campus energy loop, they're simply capitalizing on all that extra energy and using it to power some of their classroom buildings. So they are very happy with the systems here, been continuing to work with us to maintain everything, and overall the project's been a great success.
That's great. That was a wonderful, wonderful presentation. Thank you, Shannon and Brendan, right on time. So we have a few minutes for Q&A. We have a couple questions from the audience, so I'm just going to choose those. We have one from one of our audience members, Jordan Shellens, would like to know how many energy models were done through the design and construction process, and what was the program that was utilized for the energy model?
So for this particular project, we were still using eQuest, although we do a lot of ours on Energy Plus at this point. Again, the design of this was started back in 2015. We did do several preliminary, very schematic models at the beginning. As we started narrowing down our design, we kind of were honing in on one per phase, so one at DD, one at CD, and then we also had included a kind of construction model. So as we got shop drawings in and there were changes in some of the systems or some nuances, we did do an end of construction model as well. And then, as Brendan mentioned, he sweet talked our energy modeler into doing some additional calibration work. I think there was some beer exchange involved or something. But.
That's great. Our next question comes from Thomas McKinnon, who asked, what material and systems advancements are you anticipating or hoping for in the future to improve energy efficient designs and meet increased energy standards?
That's a good one.
I can take a crack at that. I don't think it's about the material or the system advancement. I think we have a lot of opportunity with what we already have. So, if we're just talking about energy efficiency, I think there's just, as a question guy, I think there's a lot of opportunity in tuning operations.
Yeah, I would say I think that actually better understanding the control of the system and being able to get more technology involved where the systems can respond fast and we can really trust that response, I think that's going to have the largest impact. We spent a lot of time verifying that our occupancy sensors were really going to trigger the systems and trying to understand how much we could let them ride in between occupancy periods. And I think as we improve that, I do hope that system performance continues to improve, but I do think our bigger bang for our buck will be in understanding how to make these controls really work.
So do you feel that regardless of the system that was chosen at the beginning, the key to getting that 196% energy efficiency or delivery back is mostly in the controls, or a big portion?
Well, so I think if we had put incandescent light bulbs in and allowed the occupants to put space heaters in and had the packaged VAV, rooftop VAV system, it would have been a lot harder to get where we were at with just PV on the roof. Yeah, yes, this building generates a lot. It's also a one-story building. So if we think about scaling this to 2, 3-story buildings, then it becomes even more important how we're doing with these system performances if we're looking at a single rooftop of generation. So I think, 1 story is a little bit of an easier challenge, but you need to at least be on the more energy efficiency side of systems to make this work as well.
Yeah, and that goes to building scale, I think, as well. There's something unique that Shannon and I were talking about mentioning here. This building presumably is completely unoccupied right now. And this building actually is unique in the fact that it does integrate real-time occupancy into the control of the space temperature. So even if the operators haven't taken into account the fact that nobody's in the building and they can set back the temperatures, this building will literally automatically do that. So that's just an aspect of the control here, which could have, you know, if you think about all the buildings that are probably operating on their normal schedule right now with nobody in them, this building is taking into account the fact that nobody's in there, and it's automatically controlling for that.
Yeah, we've actually been talking to Chris Stewart, the sustainability director who Brendan mentioned, and he is actually going to be looking to do a case study on the way this building has performed in this current crisis in terms of its response to occupancy. So that'll be very interesting.
Thank you. And we have time. We have 1 minute left, so we have time for one question and then closing remarks. So there was a question from Natalie. Shannon, you had mentioned part of net zero is not using combustion. Does net zero count how electricity is created on the grid? Is there any consideration for, does this count against the building at all? And does the college have a program to offset how the grid generates electricity?
Sure. So this particular certification that the university was looking for is provided through ILFI, and one of their rules for their certification program is that you have to be combustion free. You're allowed to use combustion during construction, but for the life of the building after that, it just has to be combustion free. They don't want you using fossil fuels locally as one of your energy sources. That said, the ILFI certification is not yet at the point where it's going to have you do an analysis of your energy purchases and what the generation profile is that you're getting from the utility. So I think that's something they'll probably take it to in the future, but it's not currently there. The university is working on bigger strategies for its whole campus. It buys power for the entire campus in one shot and then does its own distribution. So it's not a building by building thing for them. They are slowly working on building up their own renewable portfolio, and I believe they are also looking at what they can do in terms of purchasing renewable energy from their utility provider.
Fantastic. All right, well, thank you again, Brendan, Shannon, we really appreciate it. Thank you for everybody for tuning in for our first episode. We hope you can visit us next week on Tuesday night. We have a presentation from Duncan Phillips with RWDI on the stack effect in tall buildings. That's our normal chapter meeting. And then on Thursday, we have the Henderson engineers presenting fire and smoke dampers in healthcare facilities. So make sure to sign up. Make sure you answer the poll when we exit this presentation. And you should see a SurveyMonkey coming out soon. You can always visit our website for the latest info. So thank you very much. We appreciate it, and stay safe out there.
Thanks, Ben.
Thank you.